In special relativity, our space was R4 with coordinates t, x, y, z. For general relativity, we're going to need a space that reduces locally to R4 so that general relativity can reduce locally to special relativity. This is provided by the notion of a manifold. A manifold is a space that locally looks like R4, or more generally, Rn for an n-dimensional manifold. So our job is to motivate and then provide a precise definition of such a space so that it can be the arena for general relativity. So one manifold, of course, is Rn itself. That is a space that not only locally but globally looks like Rn. Another common example would be the n-sphere. That's x1 plus dot 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 squared plus xn squared equals 1 embedded in our n plus 1. That's a definition of an n-sphere. So for example, a 1-sphere is just the set of points x squared plus y squared equals 1 in R2, which we all know as a circle. We could draw like this. But we're going to think of the circle as a one-dimensional manifold. Even though I've defined it here with reference to R2, if you're living on the circle, you can only go in one direction. The interior is not part of the circle. And so we're going to seek a definition of a manifold that defines it intrinsically without reference to some embedding in higher dimensional space. S2 now is the surface of a sphere, so that would be x squared plus y squared plus z squared equals 1 in R3. Again, I'm giving it as an embedding, but it's a properly two-dimensional manifold, the surface of the sphere. And in general, an n-sphere is an n-dimensional manifold. Now, to give another example of the difference between an embedded manifold and a manifold you think of as just itself, let's think about a cylinder. So I'm going to start by giving the cylinder as an embedding. What I mean by the cylinder is x squared plus y squared equals 1 in R3. So there's another coordinate z here that can be anything. And so this defines the surface, if you like, of an infinitely long cylinder. And I'll draw a dot, dot, dot to let you know that it's infinitely long. And that's going to be also a 2D manifold. And the nice thing about this one as an example is I don't have to define it with reference to an embedding in R3. I don't have to think of the cylinder as living in some higher dimensional space. I can equivalently define it as the points in R2 where x lies between 0 and 2 pi, and I just say that 0 and 2 pi are the same point on my manifold, which is why I picked only one of them to include in the range of x. And so now, instead of thinking about the cylinder as embedded, I have just a strip here, a portion of the two-dimensional plane, where I'm thinking about just x and y, but I've added a rule that these two sides are identified. And for the purposes of a manifold, according to the definition we are going to introduce, these two are exactly the same manifold. And when we do general relativity, we're definitely going to want to think of our manifold as intrinsically defined as a four-dimensional manifold, space plus time, not some manifold embedded in some higher dimensional space, because there's no evidence that our four space-time dimensions are actually embedded in some higher dimensional space. Another example like this is the torus. We can think of the torus as some kind of donut-like thing, or we could now define it as a square in R2, where we identify both these sides with each other and the top and the bottom with each other. Okay, so the torus and the cylinder are both 2D manifolds, and we often draw pictures of them embedded in three-dimensional space, but they're perfectly good intrinsically two-dimensional manifolds because at every point on them, things look locally like R2, but globally they're in fact a little different because if you go off in one direction, you'll actually come back to the same point that you started. Let's think about how to make precise the idea that a manifold looks locally like Rn. Well, if we have a set M, and it's supposed to look locally like Rn, then in the region, call it U, where we're talking about the locally looking like Rn, we ought to be able to map it to Rn. And so we're going to imagine that we have a map from U to some part of Rn, and I'm going to draw that part of Rn with a dotted line because we're going to demand that it is an open set of Rn. And the map is going to be called phi. And this tells us that our manifold, at least in this region U, looks locally like Rn as long as phi has the following properties. The image is open, and it's a one-to-one map. So we could always take one point inside the image here and go back uniquely to one point on the manifold. It's going to be invertible in its image. And this mathematical statement that there's a map is actually a very physical thing that you've done all the time. It's erecting a coordinate system. So if we imagine our manifold is the surface of the Earth, and we're interested in describing things over here near Tucson, we could have a region like that, and we could draw our longitude lines and our latitude lines on the Earth. And the map we're talking about takes some point here, call it Tucson, and maps it to a copy of R2, since this is a two-dimensional manifold. And the copy of R2 you can think of as its latitude, theta, and its longitude, phi, and whatever numbers you assign to Tucson, its latitude and longitude, that gives you a point in this subset of R2. Okay, so that's the picture that you want to think about. These maps are really just coordinate systems that you erect in local regions. And the problem is on a non-trivial manifold like the sphere, you actually can't get away with a single good coordinate set, a single nice one-to-one map onto an open subset of R2 if you want to cover the whole space. And so for a manifold, we only require that it's locally like R2. It can differ globally like the sphere. And the way we handle that is we can have multiple coordinate systems, or in the picture over here, multiple charts. And those charts or maps can be on different regions of the manifold, but they might overlap. And so let's consider another one that I'll draw in red that covers a different region of the manifold. And now I'm going to give these an index. So this will be U beta. This will be U alpha. The map will be phi alpha. And the new region U beta will have a new map, phi beta, to a new copy of Rn. And just like for the old map, we're going to require that the image of the new map is open. So I'll draw it as a dotted line. So this thing, phi beta of U beta, needs to be open. And again, the map needs to be one-to-one so that in this image we can invert and get back to the manifold. Now, we have two charts on this manifold, and in points that are in both, we could use either chart to describe the manifold. And to make sure that we're really considering the same manifold, we're going to need some conditions on what's going on here in the overlap region between these charts. And what we're going to use is that in the images of this overlap region, which I'll draw like this and like this, we can actually make a map from the green region of the red Rn through the manifold, but eventually all the way to the green region of the blue Rn. And this map we can demand is continuous and in fact smooth. We know what that means because it's just a map from an open subset of Rn to another open subset of another Rn. And by making that demand, we have a notion that these different local Rn regions are smoothly stitched together into a good manifold. So let's see how that works. This map is going to have to start in the green region of the red Rn. So what is that green region? Well, that is the image under phi beta, the red map, of the portion of the manifold where the blue and red overlap, which is the intersection of U alpha and U beta. So that's where the map is going to start. And the map ultimately is going to end up in the green region of the blue Rn. And that is the image under phi alpha of that same green overlap region on the manifold, which is U alpha intersection U beta. And what is this map? Well, to get from the red Rn to the manifold, we have to use the inverse map of phi beta. And to get from the manifold then to the blue Rn, we have to use the forward map phi alpha. So when you do composition, you read from right to left, which means we have to do first phi beta inverse to get to the manifold. Then we compose with phi alpha to get to the blue Rn. And this map, which is a map from a subset of the red Rn to a subset of the blue Rn, we're going to demand is continuous and in fact smooth. See infinity in the advanced calculus sense. This gives us the notion that these two maps are not totally different things. They're part of the same smooth manifold. And if you manage to cover your whole set M with subset map pairs satisfying all these conditions, we say M is a manifold. And that is the precise definition. Let me write it out. A manifold is a set M together with a bunch of pairs of subsets U alpha and maps phi alpha satisfying all the above conditions and such that every point P on the set M is in at least one of the U alpha. Now some authors also add a condition that this so-called atlas be maximal. You have to include every subset map pair compatible with these conditions. The idea there is you don't want to have a different manifold just because you chose a different atlas, but that's more of a semantic issue. In this class, you just need to be able to prove something is a smooth manifold by finding a collection of subsets and maps satisfying all these conditions. The simplest non-trivial example that really will help show you what the definition is all about is the circle, S1. So let's see how this works. Here's our circle, and we're going to define it again as an embedding into R2. So our set of points, M, that's going to be a manifold, are pairs x comma y such that x squared plus y squared equals 1. Now it sounds kind of two-dimensional because they're pairs x comma y, but we're going to see that it's really one-dimensional because we're going to map the circle locally to an open subset of R1, not R2. Of course, the reason it's really one-dimensional is it's pairs x, y subject to this constraint, x squared plus y squared equals 1. So what is our map phi from some subset U of the manifold to R1 going to look like? Well, what's a good coordinate for the circle? How about the angle, usually called theta, relative to, say, the horizontal line here, y equals 0? So let's call that theta. And so our map is going to take a point on the circle and assign to it the number theta in R1. So let's think about R1. It goes on forever, but we want this map phi to take us to an open subset of R1. We need to pick some fiducial range for theta. The classic one would be 0 to 2 pi. But remember, it needs to be an open subset of R1. So we can't actually include 0 or 2 pi. We have to consider just the range between them. So phi of u is this range here. And that's just going to be the range theta is between 0 and 2 pi. Now this is one-to-one. Each point in R1 goes back uniquely to a point on the manifold, and it is open, so we have a good chart, but it doesn't cover the whole manifold. We've left out this point here. This point right there, that one special point, is not in this map, because that would map to 0 or 2 pi, but we can't include either one or both of those because then we wouldn't have an open subset of R1. So to actually make this a manifold, we're going to have to call this our first map phi 1 from U1 to R1, and we're going to need another map, which we'll call phi 2 from some other subset of the manifold to some other copy of R1. So how might we do this? Well, we can play the same trick, use an angle, but let's not use an angle that misses this point. Let's pick, some other special point, like, I don't know, maybe the vertical point up here, and define our new angle. Call it, I don't know, psi from that vertical. So to cover the whole circle, we can still take this new map to this new R1, this psi, to go from 0 to 2 pi. Phi of U2 is just 0 is less than psi is less than 2 pi. But our map to the circle maps to a different point and misses this other one here. But you can see that the maps are going to together cover the whole circle because the blue one misses the top point, the red one misses the right point, but together they're going to cover the whole circle. So we've got that our atlas is covering the circle. We've got that our maps are one-to-one maps onto open subsets of R1. It remains to check that everything properly overlaps. So we need to figure out the map psi of theta. That's the map from the red R1 subset to the blue R1 subset. And what is it? Well, from the picture, psi of theta is just equal to theta minus pi over 2, where we have to do our arithmetic mod 2 pi so that the ranges line up with the canonical ranges we've chosen, 0 to 2 pi for the two coordinates. And this is manifestly a perfectly smooth map, and so we've completed the proof that S1 is a manifold. Now, if you don't like arguing from the picture, you can also write down the equations that describe these maps. So what is theta? Well, to find theta from an ordered pair xy, you have to solve the equations x equals cosine theta and y equals sine theta. As long as x squared plus y squared is 1, there'll be a unique solution for theta, and it's exactly our red map for theta. What about psi? Well, it's the same thing, except now x is minus sine psi and y is cosine psi. Solving these equations for any pair xy with x squared plus y squared equals 1 will give you a unique number psi, which corresponds to our blue map. And now if you want to see the overlaps, well, you just compose these maps. So we set the x equations equal, and we get cosine theta equals minus sine psi. We set the y equations equal, we get sine theta equals cosine psi. And indeed, the solution, writing psi explicitly in terms of theta, is exactly theta minus pi over 2. Again, mod 2 pi to respect our canonical ranges for the coordinates. So that's how you see that the one sphere is a manifold. On the homework, I'll ask you to show that the two spheres a manifold and engage with the definition in some other ways that I think are interesting and useful. And I want to emphasize that I'm not going over the definition because I think mathematical rigor is very important for this kind of physics course. And as you know, in other parts of the course, I'm just not doing things rigorously. But in this case, the precise mathematical definition is very physical, and so it's interesting to study. And we are going to be dealing with multiple coordinate charts on a single non-trivial manifold in this course. When we get to black holes at the end of the course, we're absolutely going to have to be changing coordinate systems, using different coordinate systems to cover different parts of the manifold. They're going to overlap. We're going to use both of them. And so this abstract notion of a manifold as an atlas covering a set is actually a very physical notion that we'll talk about a lot in the course.